Welcome. Today we're doing a deep dive into something absolutely vital for India, monsoon forecasting. This is especially crucial if you're prepping for the UPSC exams.
Absolutely vital.
The IMD, that's the India Meteorological Department, just predicted an above normal monsoon for 2025, 105% of the long period average for June to September.
A significant forecast.
So we thought it's the perfect time to unpack how we actually got here, how these forecasts evolved over time.
It's a fascinating journey. The monsoon is India's economic engine, really. Impacts agriculture, policy, everything. A good forecast is critical.
Exactly. So today, we're looking at this evolution using a great report from the Indian Express as our guide.
Right. From the very beginnings, way back in the colonial era, up to the sophisticated computer models we use now.
Okay, so our mission is clear. Trace that history.
Yeah.
Let's start at the beginning. Why did India even start trying to forecast the monsoon systematically?
Well, the push really came from disaster. The IMD itself was set up in 1875, but the serious forecasting efforts kicked off around 1877.
And what prompted that specifically?
It was largely a reaction to the Great Famine of 1876-78, a devastating event. It made it brutally clear just how dependent everything agriculture, government revenue, public health was on the monsoon, especially under British rule.
So less pure science initially and more practical, almost administrative necessity.
Pretty much, yeah. The British needed predictability for their economic interests, farming, shipping, That drove the early science.
Interesting. And who were the key figures back then?
Henry Francis Blandford was important. Between 1882 and 85, he came up with this idea linking Himalayan snow cover to the monsoon rains, particularly in northwest India.
Even then, they were looking at these large-scale connections. And Sir John Eliot, he built on Blandford's work.
He did. Eliot became the first head of Indian observatories in 1889. He expanded the scope, bringing in data not just from the Himalayas, but also local weather, the Indian Ocean, even Australia, trying to get a broader picture.
But the article points out, even with all that, they still couldn't predict major droughts, like the one around 1899-1900. Why not? What was missing?
It just shows how incredibly complex the monsoon is. I mean, Eliot's work was pioneering for its time, but their understanding of the big global climate drivers, still very limited. The models were too regional, really.
Right. They didn't grasp the larger atmospheric and oceanic stuff yet.
Exactly. Local factors weren't enough.
Which brings us neatly to Sir Gilbert Walker, starting around 1904. This sounds like a major shift looking globally.
Oh, absolutely. A paradigm shift. Before Walker, the focus was mainly local or regional. Walker realized the Indian monsoon wasn't happening in isolation.
So what did he do differently?
He brought in a global perspective. He used something like 28 different parameters from the atmosphere, land, oceans worldwide.
28?
Yeah. And crucially, he identified what he called the Southern Oscillation.
Ah, the SO. That's the pressure difference across the Pacific, right?
That's the one, a kind of atmospheric seesaw. This was a huge breakthrough, linking India's climate to these massive global patterns.
And the El Nino connection to the SO, that came much later, didn't it?
Much later. Jacob Jerkness nailed that down in the 1960s. He showed they were two sides of the same coin, ENSO, the El Nino Southern Oscillation, which, as we know, is still a huge factor today. The latest IMD forecast even mentioned the helpful ENSO neutral conditions expected.
Right, so Walker really globalized the perspective. Did he also try to make the forecast more specific within India?
He did. He divided India into three regions, the peninsula, northeast, and northwest, for more localized predictions. So global understanding feeding back into regional specifics.
Okay, so a step forward. But then, after independence, Walker's models started faltering. Why would a model that worked suddenly lose its edge?
Well, the climate system itself isn't static, The relationships Walker found, those correlations between his 28 factors in the monsoon, they just weakened over time. They weren't as reliable anymore.
So the connections changed.
Exactly. Between the 1930s and the late 80s, the average errors in the forecasts became pretty large. Over 12 centimeters for the peninsula, nearly 10 centimeters for the northwest. The predictors lost their punch.
Which highlights a key challenge. Climate isn't fixed. So, to fix this, the IMD brought in the Gowarker model in 1988. How was this one different?
It was a different statistical approach. Developed by Vasant Gowarker and his team, it used something called power regression with 16 atmospheric variables.
16, down from Walker's 28.
Yes, and initially it focused on an all-India forecast, though they did bring back regional forecasts later in '99. with new zones.
And how did the Gallricker model fare? Did it solve the accuracy problem?
Well, it had its own issues. By around 2000, some of its key parameters also started to lose their correlation with the monsoon. They had to tweak it.
Oh,
And then came the big test. After a run of good monsoon years, it completely failed to predict the major drought of 2002.
wow. Missing a big drought like that must have really shaken confidence. What did that failure reveal?
It really underlined the danger of relying too heavily on past statistical relationships. I mean, if the underlying climate dynamics shift, your model based purely on old correlations can get caught out. That 2002 failure was a critical moment.
A turning point.
Definitely. So in 2003, they introduced new models, 8 and 10 parameter ones, and started a two-stage forecast strategy. An initial one in April, then an update.
Did that work?
Well, they still missed the 2004 drought.
Dear. Still struggling.
Yeah. It suggested maybe these statistical models, especially with many parameters, were prone to overfitting.
Overfitting. You mean like learning the noise in the old data too well?
Exactly, making them less flexible when faced with new conditions.
Okay, so the purely statistical route had hit some bumps. What came next? How did they move beyond that?
The next big step was the Statistical Ensemble Forecasting System, or SS, rolled out in 2007.
Ensemble, like using multiple models together.
Precisely. They actually reduced the number of parameters in the individual models down to 5 or 6, specifically to avoid that overfitting problem. Then they combined the outputs from several different models. The idea is that the strengths of different models can compensate for weaknesses, giving a more robust forecast overall.
Right, safety in numbers, almost. Did this FS approach actually improve things?
Oh, significantly. The data shows the average forecast error dropped quite a bit. It was nearly 8% in the decade before SEFS, and it fell below 6% in the decade after. A clear improvement.
That's a decent jump in accuracy. But things kept evolving, right? The article mentions the Monsoon Mission Coupled Forecasting System, MMCFS, from 2012. What's a coupled dynamic model?
Okay, so this is a really important shift. We're moving from purely statistical models, finding patterns in data, to dynamic models.
Dynamic meaning they simulate the actual physics.
Exactly. That MMCFS tries to simulate the real-world processes. It integrates data and physics from the ocean, the atmosphere, the land surface. It models how they interact to actually produce the monsoon. It's much more complex, based on the physics of the climate system.
So running simulations of the weather itself.
Kind of, yes. And the IMD started using this dynamic MMCFS alongside the statistical SEFS, sort of getting the best of both worlds.
Combining the pattern finding with a physics simulation makes sense. And then even more recently, 2021, this multi-model ensemble, MME. How's that different from the SS ensemble?
Good question. The MME takes the ensemble idea global. It doesn't just use different Indian models. It incorporates forecasts from various major climate prediction centers around the world.
So pooling international resources.
Pretty much. They take India's own MMCFS results and combine them statistically with outputs from models run in the US, Europe, Japan, etc. The thinking is that averaging across many different complex global models helps cancel out individual model biases and errors, leading to an even more reliable forecast.
A global team effort for India's monsoon. And has this MME approach paid off? The article mentions error reduction.
It seems so. Looking at the period since 2007 when SEFS and then MME came in, the overall absolute error in the seasonal forecast is down by about 21% compared to the earlier period, like 1989-2006.
21% reduction? That's substantial.
It is. And even the first forecast they issue in April has become much sharper. Since 2021, the difference between that April forecast and what actually happened has only been about 2.27 percentage points on average. That's well within their target error margin of 4%.
That's impressive progress, considering where things started. So, where are we now? Is the system pretty much perfected, or is there still room to improve?
Oh, there's always room for improvement in climate science. Experts point out that even the sophisticated dynamic models like MMCFS have their own subtle biases or systematic errors that can be worked on.
Right.
And another area is improving how these models capture teleconnections.
Teleconnections, those long-distance links, like INSO influencing India.
Exactly. Making the models even better at simulating how those global phenomena impact the monsoon could lead to yet more precision. The science is definitely not standing still.
So the quest for the perfect forecast continues. This has been a really great overview of that whole journey.
It really has. From Blanford looking at snow, to Walker seeing global links, to today's supercomputers running coupled models and global ensembles. It's quite a story of scientific progress.
And for you listening, especially if you're tackling the UPSC syllabus, you can see how deeply this connects, right? Indian geography, the economy, agriculture is huge, disaster management, water policy. This is all aligned to the monsoon. Understanding this evolution, how we got these forecasting tools, gives you really valuable context for analyzing current affairs, policy debates, economic planning. Definitely a key area for mains and prelims both.
Absolutely. And maybe a final thought to leave you with. We've talked about progress, but we also know climate change is making things more complex, maybe less predictable in some ways.
That's true.
So looking ahead, what new innovations might we need? Could AI play a bigger role? Do we need even better ways to feed real-time data into the models? How do we capture regional climate shifts more accurately? It's a big question at the intersection of tech, data, and climate science.
A very relevant question for India's future.
Yeah.
Well, if this deep dive was useful for your studies or just piqued your interest, do give us a like, subscribe for more, and please comment if you have questions or ideas for other topics you'd like us to cover.
And just to reiterate, the basis for our discussion today was a recent report in the Indian Express.